have, what is this, 9.2, 9.3, and then chapter 10? Okay, so this is your last test of the year.
Did you say it's short?
Is it short, the test? I'd say it's average length. It's not as short as the last one was shorter. It's not as short as the last one was. Okay? It's both, for sure. There's definitely math and conceptual. If you remember, we did a lot with math in 9.2 and 9.3, and then in 10.3. 9.2, 9.3, and 10.3 involved math. But 10.1, 10.2, and 10.4 did not involve math. So let's start with chapter 9. Let's go back to chapter 9. I was just listening to a bunch of your lab submissions last period. You guys made me laugh, by the way. I'm not going to call people out individually, but I'll call you out as a group. Some people decided that Bernoulli's principle was Bologna's principle. That was a pronunciation I heard today. I was literally laughing at my desk, and everybody around me was like, "What are you laughing at?" And I hear somebody go, "In Bologna's principle," like Bologna's principle, or the continuity equation apparently was like the it was like continuity. I don't know what it was, but somebody pronounced it like a crazy pronunciation. But in 9.2 we talked about the continuity equation, and then Bernoulli's principle is the other one. But anyway, that's back to what your lab was on. So let's take a look and think about what we had there. So the continuity equation, what did it say? What did the continuity equation say, Sam?
That the fluid has a constant rate, and that the A1, A2, B1 is equal to A2, B2.
Yeah, very good. That the fluid has a constant volumetric flow rate. That's the first theoretical part of it, right? It means that the same amount of volume is flowing through the pipe at any given point in time, at any given location in that pipe. Now, the second part is the mathematical portion behind it, which tells us A1V1 equals A2V2. And a lot of you demonstrated this in your lab by simply adjusting the area of the cross-section of the pipe and dropping the speedometer in place and saying, oh look, the speed picks up. And that's absolutely right. The easy example to remember is to take your thumb, put your thumb over the end of a garden hose. You're reducing the area, thus you're increasing the velocity. Okay? A1V1 equals A2V2. 1 and 2 represent the first location in the pipe, and 2 represents the second location in the pipe. Okay, so remember that you have some sort of internal flow occurring here. This is at the first location, this is at the second location. Let's see. I'm trying to think of other stuff with the continuity equation that we spoke about. We then went on to talk about Bernoulli's principle, and we specifically talked about Bernoulli's principle and how it's related to this. What was Bernoulli's principle? What statement did that make? Shimon?
It says that as something increases,
Anybody else? Somebody said Sam. She just answered the last question. What else? Come on, people. Bernoulli's principle. Nobody? You better study. What do you got, Tom?
It's the more volume you have, the less pressure there is.
Not volume, Tom.
Velocity.
There it is. Velocity. The more velocity you have, the less pressure at that instant in the pipe. And this one was the one that was a bit, I guess you could say, counterintuitive, simply because of the fact that when you look and you think about this physically, and you take your finger and put it over like the end of a garden hose, you think, oh, I'm like building up pressure. So pressure coming out, the water coming out has a lot of pressure. We are building up pressure, but the pressure building up is behind that location. So the location before your thumb has a lot of area, and if it has a lot of area, it has a low velocity. So there's very little velocity there. The pressure is all built up behind your thumb. The water coming out that sprays past your thumb with a higher velocity has a lower pressure. A lower pressure. There's a cool trick you can do to see this, actually. I forget how to do it. Mr. Donachek showed me something about it last year. And the whole concept behind it is that the flow rate of the actual fluid causes a pressure differential. And you can do it, what did we do with last year? It's obvious, the easy or the obvious way to think about it has to do with like your shower curtain when you're showering. But the easier example to explain it is you run the water, and then if you bring a charged rod near it, the pressure causes it to move left to right, the actual water flow will change. But if you think back to what was it, static electricity, when you build up static electricity on your body. Have you ever been in the shower and the shower curtain kind of like sticks to you? It's not like staying where it should be like along the edge, but it kind of like leans toward you. It's not just static electricity, but it's also the flow of the water causing a pressure differential, which causes the shower curtain to actually get pulled inward. That's why when you like step under the shower and like you're actually getting the water hitting you suddenly, the curtain flows back to where it was. It's because you're changing the actual flow. But the minute you move away and the water's flowing, you can see the curtain start to actually come inward. But that's also because of Bernoulli's principle. But the way we went through it in class, if you remember, had to do with the actual pressure differential. What else in 9293? I'm trying to just look at my notes to see what else I want to add. What were some other things in 9293 that either confused you or you want to ask about? Or Siobhan?
We talked about Pascal's principle in 92.
We talked about Pascal's principle, which said what?
It says that pressure applied to a fluid in a closed container is transmitted equally throughout the thing. So basically, you're pushing down something like it's like the egg. It's basically if you squeeze the egg, it's not going to crack because you're applying the same amount of force to all sides.
Yeah, and what did we use that concept and apply it toward? What topic? What application did we make toward this? And?
Hydraulic press.
Yeah, hydraulic presses. And if you recall, you think of a hydraulic press as a apparatus that has a larger and smaller area of loading. One which you're going to push down on. So you apply some force to some piston. The piston moves down. The piston applies the force to that pressure, to the internal fluid, which exerts pressure on this side with a larger area over here. And what the hydraulic press allowed us to understand was the following. Since the pressure throughout a closed system in the fluid is the same, this was the equation we came up with. Okay, that was the equation right there. F1 over A1 equals F2 over A2. Because if you remember from 92, in 92 we talked about what pressure physically is. Pressure is force over a given area. So I did the simple example. Tom came out. Remember, Tom, when you were jumping across the room, we were talking about pressure? And that concept that I gave, I said, like, just stand on one foot. You're doubling your pressure. Lift this one foot up and stand on like your tippy toes. Now it's like quadrupling the pressure because you cut the area in 4. So we see that pressure and area are related to each other, but they're indirectly related. Okay, pressure, oops, let's write it in the middle. Pressure equals force over area. That's why I can replace this P1 with F1 over A1 there. But we'll see that the pressure is indirectly related to the actual area over which this force is applied. The more force, though, the more pressure. That's logical. A lot of you gave great explanations in your videos in the lab that a lot of people said, like, oh, you know, the pressure increases with depth. And here's physically why. It's really because there's more force above you, and that's exactly right. There's more water above you when you go deeper into the water. There's more force above you. There's more force. There's more pressure. Right? What else in 9.2 and 9.3? I'm trying to think.
Pressure varies with depth.
Pressure varies with depth. So we talked about this formula. Let's write that one out. Thank you, Siobhan. So we have this formula which says P equals P0 plus rho GH. What, first of all, is this titled, actually? When I'm looking at this, what pressure is that? As opposed to the pressure of this is called something and this is, they're each called something. Ant, give me something.
PO is the atmospheric pressure.
Okay, that's the atmospheric pressure. Agreed. Sam, what else? P is the total amount of pressure. Very good. And last? Chris?
The rho GH is the gauge.
Gauge pressure, which is? Yeah, the pressure within the actual system, the fluid itself. So if you think about that lab, when you turned off atmospheric pressure, if you remember, suddenly the pressure in the water dropped, and it dropped by 101.3, because PO is literally 101.3 kilopascals. Kilopascals.
Is that constant?
It is, but it's in kilopascals. So what did I put on your formula sheet, actually? I probably put 1 times 10 to the 5th, I think, right? Take a look, somebody. Let me know what I put. What do you got? At the bottom of the formula sheet, at the very bottom, what do you got, Ant?
1 times 10 to the 5th.
Okay, so I wrote this as 1 times 10 to the 5th because it's 101.3 kilopascals, which is 1 times 10 to the 5th pascals. Okay, that's a constant. You don't have to memorize that. That's the actual pressure that the atmosphere pushes down onto it. You should understand the physical nature of this stuff, though, right? Although necessarily you don't have to memorize it, you should still know what PO is, not just being able to plug it into a math problem, physically understanding. So the total pressure in object fields is the atmosphere plus whatever the pressure is from the fluid it's submerged in. So if you're underwater, you're feeling the atmosphere pushing down
Height
and
times
the
gravity.
gauge pressure.
Height times gravity times.
What does H actually stand for, though, really?
Depth.
Depth. Depth. Okay, not debt.
Depth.
Not DEBT like you said in your video today. I heard in your video when I was listening. You said, then the debt goes down. I'm like, oh, the debt, that's great. It's solving your economic crisis. The depth, increases as H increases. H is the height of water above that object, really, which is the depth. Okay, the height of water. What else? Let's see. Anything else? I talked about laminar and turbulent flow. Is that what you're going to mention? Yeah, I talked about laminar and turbulent flow. And laminar flow is predictable, streamlined flow. Like if you had flow through a pipe that was nice and smooth. Turbulent flow, you think about the river with the rocks. After the rocks, like whitewater rafting, you have all those little currents, those riptides. Those little riptides, that's turbulent flow. What number do we use to know if we have a turbulent or laminar flow? What number is that?
The Reynolds number.
The Reynolds number. Okay, forget that. That's sad. You got a classmate with that name now, right? So the Reynolds number. Yeah, Tom, if you get it wrong, then I'm just gonna be like, oh man. So the Reynolds number tells us whether a fluid flow is turbulent or laminar. Above a given value, it would be considered turbulent flow, meaning it exceeds what we have as a limit. If it's below that limitation, it's laminar flow. Okay, so you calculate again what's called the Reynolds number is the calculation you do to do this. I did not ask you to calculate the Reynolds number. You're not going to have to, but I want you to theoretically understand what we're talking about.
Do you want to know the,
All right.
ideal fluids?
Ideal fluid, you should know the term, yeah, absolutely. An ideal fluid is a fluid that is assumed to be what? Three things. Three things for an ideal fluid. Give me one of them.
Non-viscous.
Non-viscous, meaning it flows easily. It's not like, remember molasses and syrup was the example of something that's viscous? So when it's viscous, it flows very slowly, not smoothly. Yeah?
I was going to say predictable.
So laminar, good. Non-viscous, laminar, and incompressible. A fluid that cannot be compressed, cannot have pressure applied to it and changing in volume. Okay, something that can be compressed, you can literally do that. You can compress it.
Should we be able to say what they're used for? Because you mentioned it, probably from your videos.
Yeah, I mean, for example, ideal fluid flow is, any type of internal fluid in pipeworks and piping systems is assumed to be ideal fluid flow. Whereas, if you think about aviation with airplanes and rockets, it's not going to have ideal fluid flow. Yeah.
So, just in general, a fluid that would be compressible would be a gas, and
Yeah.
incompressible would be a liquid.
Very simple example, in general, but there's definitely exceptions to those rules. Okay? So there are some liquids that can easily be compressed, even though they're not a gas. But most gases themselves can be compressed. I don't think there's any gases that wouldn't be able to be compressed, but under a certain amount of pressure, the temperature might skyrocket for that gas. I still don't think there's limitations. It's just you'd have to have a container that can withstand that much pressure.
Just in case we run out of time, what will the math problems be like? Because there's a lot of converting your
You could expect for math something with 9.2 and 9.3. So continuity equation, hydraulic press example. These are not lengthy problems, right? They would be like 3-pointers, but they'd be math parts. Hydraulic press, pressure, what we just did on the board that's there right now. And then something with temperature change / phase change, that kind of thing. What we did the other day with the amount of heat necessary to heat up.
That would be a long.
That'd be a longer math problem at the end, yeah. You should understand the differences in your, let's jump to chapter 10 now actually, because we're at the point where you should. In chapter 10, you should understand the differences between your, let's see, absolute and your regular scale. So Rankine and Fahrenheit differ. Rankine scale is the absolute scale for temperature. And then for the other one we're talking about, Kelvins versus Celsius. What was absolute zero again?
0 Kelvin.
What does it mean though? What does absolute zero actually mean?
When movement was there's no movement.
Yeah, there's zero kinetic energy of the particles, so they're not moving, which is impossible. And there's always some motion of the particles. What else for temperature? We talked about 3 modes of heat transfer. Conduction involves contact. Convection involves fluid flow over a surface. Radiation involves heat radiating in energy, or as energy particles. What else did we talk about? We talked about how heat transfers, always from where to where? Hot to cold. Always hot to cold. We talk about thermal conductors versus insulators. This metal is a good thermal conductor, so it feels cold because the heat is transferring very easily from my hand to the metal. This is a good thermal insulator because heat is not transferring easily from my hand into the wood. Okay, different materials have different insulation and conduction values.
Oh, wait. What? Sorry.
Sorry?
What is superconductor feel?
That has to do with the electrical
Oh,
conductivity.
okay.
Yeah. I'm sure that there are things that are very good conductors of thermal energy also that would be considered like superconductors for thermal. But yeah, I mean, they would feel extremely cold then because the heat can transfer very readily that air. Yep.
I feel like those are more watching.
Yeah, I don't know. I wonder. I mean, it would be something that would like draw the heat out of your body almost. You know what I mean? Some sort of material that's so endothermic, it absorbs so much heat that it sucks all of it out of you.
Sounds like a science fiction.
It does. It sounds like those like fantasy books or movies you watch or read where like somebody gets stabbed with something and their body like solidifies in the ice, you know? Something like that. I don't know.
I was thinking like your soul gets transferred into this metal and you become part of the
Something like that. Along those lines. Let's see what else there is to know. What's that?
Are you doing the other section?
Oh, thermal expansion. Yeah. Thermal expansion. What is thermal expansion?
like somebody repairs it.
Temperature increases and electric volume.
Yeah, temperature causing a volume change.
Extra water.
So change in temperature causing a change in volume. Yeah, it's a good exception is water because of the hydrogen bond that exists in water. So it's one of the few that when you cool it further beyond its liquid phase into its solid phase, it actually expands. Whereas most objects, when cooled from a liquid to a solid, contract. They don't usually expand. Let's see. How much time do I have? Time check.
3 minutes.
3 minutes. Thank you. Yeah. What kind? Hydraulic lift problem? Okay. So let's say you have a hydraulic press and one side of it has a cross-sectional area that's unknown, but you do know that the radius, it's a circular piston, or the circular loading zone, the radius is 3, well, let's say it's a huge lift, 3 meters. And we know that the force being applied on that end of the lift is, or the force that has to be supported, at least we could say, is 3,000 newtons. On the other end, you've got a piston that's really small, so that's the big end. Oops. Hydraulic lift. So Pascal's principle. On the other end, you've got a radius of only 1 meter, and the question is, how much force do you need to apply to it in order to lift the other side? So you start right away by recognizing that we have areas that are involved in this formula, but we're only given radii. So use pi r squared to find the areas for each one. So right off the bat, it doesn't matter because they're going to cancel. That's all right. I was predicting that question, by the way, when you raised your hand. Did you see me go like this? Because I had a feeling you were going to ask about pi. So we have the actual force over area equals force over area. F1 is 300 newtons. A1 is pi times 3 squared. F2 is unknown, and A2 is pi times 1 squared. Please cancel pi's. It's going to happen a lot where the pi cancels on both sides. If it's both in the denominator, they both cancel. So 300 over 9 will be your answer, because this is just going to become a 1 on the right side, right? It'll just be 1 squared in the denominator. So 300 divided by 9, what do we get for that? $300 divided by 33 1/3?
Is there a problem set?
There is not. There's no problem set due for this test. So what do you think you should do, honestly? Yeah. If you want to, I can give you suggested problems. Okay, would that be useful?
Email us.
I'll email you out a list of suggested problems in chapter 9 and 10. Okay? All right, tomorrow, again, remember, come in, check in, get your stuff, head right to the jug yard. Anybody know about the weather for tomorrow? Is there rain on the forecast?
It's gonna rain.
No rain dances tonight. No rain dances. Whatever you normally do, no rain dances tonight, please.